So, as promised, super cool example. We're going to use our surface area formula to figure out the surface area of a sphere. So, let's draw a sphere. Always helpful to have a picture. And we're going to do the same thing as we did with our cylinder. We're just going to find the surface area of the top half of our sphere, and we'll be able to multiply that by 2 to get the whole surface area of the sphere. Let's call the radius big R. That way we can reserve the variable little r. We will use it, so we're going to have radius big R. And then remember that the formula for the equation of a sphere is this: x squared plus y squared plus z squared equals r squared. We're going to put the origin here, so we'll put x-axis, y-axis. I like drawing them this way. Some people do that rotated. XYZ there. So if we're just doing the top half of the sphere, then we're taking z equals the root of r squared minus x squared minus y squared. Okay, and then we need fx and fy. And by the way, z is also f of xy, right? We need fx and fy for the formula. So this is going to look a lot like the previous one. So we'll have 1 over 2, and then this is power of negative 1/2, so it's a root in the bottom. And then we do the chain rule, taking derivative with respect to x, so that's negative 2x there. So the 2's will cancel, and we'll get, let's switch back to black, I meant to do that. We'll get negative x over the root of r squared minus x squared minus y squared. Okay, and then fy is going to turn out to be much the same thing, so we'll get negative y over the root of r squared minus x squared minus y squared. If it's completely symmetrical, you don't have to do the work again. You know it's going to be the exact same thing. Okay, so then my surface area of half my sphere, I'm going to integrate over, we'll call it d this time. D, by the way, is just going to be, if you look in the xy plane, the circle of radius r. Okay, and then we'll have the root of fx squared, so the negative won't matter, r squared minus x squared minus y squared, plus fy squared, negative won't matter again, y squared over r squared minus x squared minus y squared, plus 1. We'll just write dA for now. Okay, so what's going to happen once we find a common denominator, this will be an r squared minus x squared minus y squared over r squared minus x squared minus y squared. So then once everything in the numerator cancels, you actually end up with r squared here over r squared minus x squared minus y squared dA. And then this is just begging for polar coordinates, because I don't want to integrate over the circle. Sorry, shouldn't put a circle around a circle. I don't want to integrate over a circle and figure out what the bounds of x and y are. I just want to do this in polar coordinates. It'll be way easier. So remember my conversions, little r squared equals x squared plus y squared. Also, this is a root of big R squared, and big R is positive, it's the radius, so I can take that out. In fact, I can take it out of the integral entirely. Okay, so then I'm just left with 1 over the root of r squared minus little r squared, and then I'm going to have an r dr d theta here. And then my r, so I want the whole circle, right? So my r is going to go from 0 to big R, and my theta is going to go from 0 to 2 pi. That'll get me all the way around the circle. Okay, now I can integrate. And this is not a bad integral. I need a u substitution. So u is, I'm going to make it r squared minus r squared. So then du, big R is a constant, so that'll be negative 2r dr, not d theta, dr. So then r dr will be negative 1/2 du. Okay, so I can make my substitution now. I have a big R out here, integral from 0 to 2 pi, currently integral from 0 to r. This will be, I'm just going to remind myself that these are bounds for little r equals 0, r equals big R. And then this is 1 over the root of u, and then r dr was negative 1/2. Okay, so I have a negative 1/2 out here, du, d theta. Okay, and then big R out here, 0 to 2 pi, I can integrate now So I'm going to increase the power by 1, so that's u to the positive 1/2, and then divide by positive 1/2, so this 1/2 goes away. So it's negative root u, and then I'm going to replace u with r squared minus r squared, as r, little r, goes from 0 to big R. And then I have a d theta here. Okay, so that's big R, integral from 0 to 2 pi. Plugging in big R, I get 0. Plugging in 0 for little r, I get negative root of r squared, which is negative r, but I'm subtracting because it's the bottom bound of the integral. So I end up with actually a positive r d theta. Okay, so I can take that out or leave it in, doesn't matter. I have r squared theta. Theta goes from 0 to 2 pi, so I'm left with 2 pi r squared is half the surface area of the sphere, and so surface area of the whole sphere is double. And if you remember from high school geometry, they made you memorize these. You can now prove them all. Surface area of the whole sphere is then 4 pi r squared.